Let me introduce the speaker. So JC is a professor at Simon Fraser University, Canada, and he's a fellow of the Canadian Academy of Engineering and an IEEE fellow. He received BEng from Tsinghua University and PhD from Hong Kong University of Science and Technology. And he served as the editorial board of IEEE SEM transaction on networking, IEEE transaction on multimedia, IEEE communications, surveys and tutorials, and IEEE Internet of Things journal. He was a steering committee member of IEEE transaction of mobile computing and steering committee of a share of IEEE ACM QoS. He was also TCP co-chair of IEEE Infocom 21 and general co-chair of IEEE Infocom 24. And he's the presentation will be joined by Sami, and he's a third-year PhD student in computing science in Simon Fraser University as well. His research focus on networking solution on low Earth orbit satellite networks for computational offloading and for computer vision solution. Previously, he worked at LTView system as a software engineer, setting up and maintaining automated build systems. And he received his bachelor degree from computer science and Simon Fraser University 2029. JC, the floor is yours.
Okay, yeah, thank you. I will share my screen. Yeah, can you see it?
Yes, we can.
Okay, yeah. So basically, I'll be talking about some of our measurement studies on the performance of LEO satellites, and in particular, Starlink from end user's perspective. And this is joint work with my PhD student, Sami. So for me, I will provide some background about this research project. It's actually within a large project, and the network is part of it. And Sami will then talk about more details on the measurement. So the thing is that starting from 2020, we have been working with various groups, including the Fishery and Ocean Canada, Pacific Salmon Foundation, and the various First Nations in the northern British Columbia and Yukon to do the underwater salmon monitoring. So salmon return to those rivers in the remote areas every year. And then it's necessary to count those salmons underwater so that we know how to preserve them. And it's also very important to the fishery industry in British Columbia. Okay. As you can see, most of these kind of sites in the remote areas, and this is a challenging work, and this leads to the so-called the Salmon Vision project between us and the biologists in Simon Fraser University, and as said, also funded by many other research groups and foundations, in particular Pacific Salmon Foundation. And it's also reported by CBC, so it includes the cameras, the Internet of Things, and also you have to deliver data to the data centers in Vancouver for further processing. So this is a vast land from Vancouver, actually from all the way south to Portland, California, and then north to Yukon and also Alaska. A vast land, most areas actually are not even habitated, and not to mention with communication infrastructure. Okay. So taking one site as an example, the Kauai River, which we have been there, it's almost 500 kilometers from Vancouver, and the trip includes a 2-hour flight and 2-hour jet boat and 2-hour small boat to the measurement site. And there's no permanent residence there. And of course, there's no power grid, no communication infrastructure. So to move the data from these sites to the major cities where we have cloud data centers, we may have to rely on satellite, okay, but on the other hand, we have seen a lot of challenges in this kind of remote areas and challenging areas. One thing, of course, is power, okay. So as said that in the wild, you don't have those power grid with persistent power supply. Often the case, you have to rely on batteries and solar panels. And actually in the past, they have geostationary orbit satellite, YSAT-2, and they have 4 300-watt solar panels. Even with that, sometimes they have problems. And not to mention when you have winter, the bad weather, the snow will cover the whole solar panel. You don't have power at all. Okay, that creates a big challenge. And also, we have the environment challenges. The site is in the Great Bear temperate rainforest, and we have trees. Most of trees are 30 meters tall, and you have wildlife, black and grizzly bears. Okay, you can have a look at this site. In fact, there's almost no way you can install satellite dish. Okay, and the trees are fully covering this area, and they are very tall, and there's no open space. The only open space would be this river, and you have a wheel across this river, but where to install the dish remains a question. So you install on the wheel, but that can be flooded by water, that can be destroyed by bears. So that's another challenge we have been facing. Okay, and that's a closer look about the wheel and also the solar panels on the site. Okay. There were some other issues. The land is actually the homeland of the First Nations. They have their own culture, whether they want to move the data outside of their sites or whether they want to have network communications actually in their land. That's actually another problem. Okay. So having all these kind of problems, Sami will talk about our network configuration, the observations from this use case of satellite in the wild. Okay, yeah, Sami, you can continue.
Yeah, okay. Can everyone see this slides?
Yes, we can see it.
Okay, so after a potential use case, let's go back to talk about low Earth orbit satellite networks. And just to quickly go for a background, satellite networks provide a basic sense of network connectivity by sending radio waves to satellites in space and then back down to Earth to establish ground stations. And for satellite orbits, there are three major types, from furthest to shortest: geostationary, GEO, 35,786 kilometers; medium Earth orbit, or MEO, at below 20,000 kilometers; and then low Earth orbit, which LEO, which is between 160 to 2,000 kilometers. And as you get closer to Earth, each satellite covers a smaller area. Therefore, LEO satellite networks are made up a constellation around many nanosatellites that cover all around the Earth. This close distance allows the connection to have a lower latency and higher throughput without needing long network cable infrastructure to connect to remote areas to the internet. And as we've seen, there have been several corporations that have deployed low Earth orbit satellite networks, or LSNs, such as OneWeb and SpaceX's Starlink. OneWeb has previously built a constellation of 648 satellites, where Starlink has already established more than 2,000 satellites. And we'll focus on Starlink for our measurement study, since they have a consumer product and relatively established. And as you can see here, the first shell of Starlink is depicted in this picture and shows these Starlink in a constellation covering the Earth. And Starlink has been approved by the Starlink has been approved by the FCC to launch more than 12,000 satellites recently and may harbor up to 30,000 in the future. So I'll talk about a few terms that we'll use for satellite communications. There are user links, which is the okay. The user links, the ULs, describe the communication between a customer Starlink dish and an overhead satellite, and what is called ground station to satellites, or GSLs, describe communications between a satellite and an established ground station, and that can serve then as a gateway to the internet. And intersatellite links, or ISLs, that describe communications between satellites that can often allow greater distance speeds traveled. And then the bent pipe communication, which previous has been described as well, which describes either from UL to GSL or GSL to another GSL, which can visualize an actual bent pipe. So our motivation for doing the measurement study was to discover whether there was a practical performance for Starlink that's comparable to a typical terrestrial network, and discover what influential factors in Starlink network services that it can be perceived by end users, and to see whether Starlink has achieved a global coverage. If not, what would be the challenges? And of course, the usability of Starlink for offloading for our Salmon Vision project that we mentioned. And so here would be the structure for the rest of this talk. I'll start off with comparing a few related works to our measurement study at the time and describe the measurement topology and methods, including the data we have gathered, and then the observation insights of our analysis of the measurement data and how the Starlink would perform in remote wild areas, as well as we did a small mobility analysis of a standard Starlink dish, and then talk about some potential social impacts that is from established LSNs. And I'll conclude with some thoughts for the future. So for related works, many measurement works have existed for regular terrestrial and mobile networks, but there have been limited rework measurements at the time on Star LSNs until recently. So there was works on simulators for LSNs such as Hypatia and StarPerf, which provide a good model and design validations, where we need actual real-world measurements to provide a frame of reference and discover issues that may not have been anticipated with simulators. So there have been a few measurement works on Starlink that was published in parallel with our work that measure Starlink using a browser extension, Ookla speed test, using Quick to measure its performance. For our study, we considered a larger global coverage of distant endpoints with consideration toward video streaming remote wild northern areas and power consumption that was not covered in these parallel measurement works. So for our measurement topology, we deployed a Raspberry Pi and a lab computer to perform the measurement for Starlink dish and the terrestrial network. The Raspberry Pi measured Starlink, while the lab computer measured a typical asymmetric terrestrial network with around 800 download and 150 upload. We tested the throughput and latency through the software tools iPerf3 and Cubic TCP, and used ping to 9 different regions worldwide. We also did some video streaming experience with YouTube by playing back a high-definition 8K video and monitored the buffer health. And as I'll discuss later, we discovered that Starlink was only using a single bent pipe framework, as shown here, where it only serves as the first hop to communicate to the internet, or the last hop when getting data from the internet. So our measurements lasted half a year from January 2022, collecting over 3 million records per region. And we measured 4 Starlink dishes, 2 in Burnaby, which is east of Vancouver, 1 in Coquitlam, which is in the northeast, and another in the far north of Kauai Point. So as stated, that Starlink at the time worked only as a single bent pipe framework, and we found latency patterns in a routing strategy that suggests this. We used traceroute and found that all destinations, such as to Europe and North California, always routed to the closest ground station to the dish in Seattle, with the next hop being a USA ISP instead of for the Europe destination routing to a ground station in the east of US instead. We also observed that ISL likely was not yet deployed, as the marine-focused Starlink only works within coastal waters, whereas if ISL was properly deployed, communications to the middle oceans should have been possible. And here are some results from our latency measurements in this cumulative distribution latency graph. The terrestrial network and Starlink is separated by destination regions these are AWS servers. Starlink on average has a latency that is 10% higher than the terrestrial network, but is much more unstable. Most of the time, Starlink would always be above the latency of the terrestrial network, suggesting that there are very few number of hops that cause this delay. Otherwise, a multi-bent pipe transmission would cause a much larger latency discrepancy when connecting to further away regions due to having less hops, as the transmissions can travel further away using the satellites. We also discovered a moderate correlation of 0.5 calculated with Pearson correlation in the latency across the regions, suggesting that the routing strategy is very similar amongst the destination regions. And here are the averages of the throughput that we measured comparing the networks across all the regions. The dark bars refer to the terrestrial network, and the lighter bars are the Starlink, with the straight lines in the middle of each bar representing the standard deviations. The Starlink TCP download throughput averages around 80 megabits per second. However, it is often much less stable compared to the terrestrial network, likely due to the moving dynamic satellites and potentially low quality ISP routing after being passed over from the Starlink network. We also discovered that Starlink had issues with the TCP cubic congestion control, where the bandwidth utilization, describing the ratio between TCP and UDP, is of 39%, as opposed to terrestrial networks 46.8%, suggesting that the cubic TCP is sensitive to the dynamic satellite hop. And for salmon monitoring, we would require video analytical services that upload videos from cameras to remote servers. This would be an upload-centric demand, which is conflicting with the Starlink's download-centric design. And to further review Starlink's uplink live video streaming performance, we streamed videos at 10 FPS from a Starlink client to a nearby data center, considering two different uploading modes. The first involves uploading H.264 compressed videos with RTMP, which here we refer to as VC. The second involves uploading JPEG compressed frames independently, one by one over TCP, referred to here as IC. And here the figure shows the end-to-end throughput distribution across 20 in-the-wild trials, with the numbers describing the bit rate in megabits per second. As shown, it can be challenging for today's Starlink to support RTMP-based video uploading at higher bit rates, such as 6 megabits per second here. And this significant throughput variation for the same video can underscore the substantial impact of underlying network variations on application perceived quality of experience. Additionally, supporting high frame rate synchronous offloading for applications with stringent single frame response requirements, such as augmented reality applications, remains challenging for today's Starlink. And of course, the environment can be a great factor that can affect the dish. One of them is obstructions, which can come from basic obstructions from nearby trees blocking radio waves, or weather, especially thunderstorms and geomagnetic storms. We found that thunderstorms causes 420% more frequent and prolonged network outages compared to clear days. This makes Starlink network rather unusable during adverse weather, posing challenges for deployment in temperate rainforests known for their humidity and cloudiness. For geomagnetic storms, they happen during solar flares colliding with our atmosphere, which has happened during one of our measurements, which dropped our throughput drastically down to 5 megabits per second. This could be an important factor to monitor for to provide good Starlink uptime. In normal rain and precipitation, there is actually a downward trend that exists as for throughput as precipitation increases, as can be seen in these graphs. On average, we found that throughput declines by 27% during any form of precipitation. We found that there are works that describe that clouds can lower the signal strength of radio waves that Starlink uses, which affect the service quality. For in the wild Starlink usage, we ran some tests with Starlink at the northern region near a lodge in Kauai Point, built by the Heiltsuk people. The throughput is actually 68% lower than the dish in Burnaby, and latency is around 11 to 30% longer with more frequent outages, suggesting that not many satellites and ground stations were able to cover these northern areas. Our second test at a remote location is inside a valley with tall hills surrounding the area at Manning Park. This area was actually stated not to be officially serviced until the end of 2023, as evidenced by what we observed as extremely poor services despite being able to connect to satellites. We observed a 90 to 350 milliseconds of delay with only 13 megabits per second of throughput on average. The large hills and mountains may have had a part in disrupting the service quality, which will require more satellites to focus on covering such an area. For this test, we relied on a 1500 amp hour power pack, which allows Starlink to work for about an hour. We also performed a case study in Franceville, Africa to study their network infrastructure. We found that the performance of their current cellular network in Franceville is notably inferior to the LSN services that we have experienced. The average download and upload speeds are 4 megabits per second and 0.27 megabits per second, respectively, with a latency of 303 milliseconds and a jitter of 89 milliseconds. Many of the small villages in Franceville face difficulties in receiving signals on their mobile phone and often require use of signal amplifiers. Deploying a Starlink dish may be beneficial. However, inadequate electrical power supply in these areas could pose potential challenges in doing so. And here you can see the top two images show the Kauai Point, where the bottom two is the Manning Park. Here you can see in Kauai Point there is a clear sky, whereas in Manning Park it is surrounded by hills and mountains that surround the valley where we deployed our dish. We've also ran some mobility tests with Starlink by strapping the standard dish on top of a minivan and performed a 30-minute mobility test driving 40 to 70 kilometers per hour around several turns and corners and a straight run at the end. We found that Starlink does work while in motion, but has a long way to go to match the stationary setup. The data was gathered from measuring both latency and throughput directed to a North California AWS server. The top graph shows the latency and the bottom is the throughput, with the vertical lines describing the 95% confidence intervals. We found that the connection is unstable and with frequent outages. Where the high latency and the gaps in the throughput chart denotes this. The latency spikes higher than 200 milliseconds twice per minute on average, and the upload throughput is actually relatively normal at 5 to 10 megabits per second. However, download throughput is rather inconsistent, dropping frequently from 100 megabits per second to 50 or even 10 megabits per second. This service quality may work for applications with large buffers such as YouTube, but any applications that require low latency and consistent throughput cannot be used with Starlink in motion. There have been recent deployments of Starlink RV dishes that exist for mobility applications, but we have yet to acquire and test these new dishes. There have been also some considerations of the potential societal impact of the global coverage of LSNs. LEO orbit and spectrum resources operate on a first-come, first-served basis, giving Starlink a significant advantage due to being one of the first pioneers to launch so many LEO satellites. There has also been a presence of many space debris in orbit that poses some risks to Starlink satellites, and Starlink satellites, to avoid collisions, perform frequent collision avoidance maneuvers, with their frequency potentially increasing exponentially over time as the space debris increases. Starlink satellites are too bright when illuminated by the sunlight, which can also potentially hinder telescopic observations. And there's also Wi-Fi pollution in the social aspect, where there are concerns raised among biologists that we have conversed with, that it could distract, that mobile applications could distract and compromise attentiveness and self-reliance that are essential for survival in remote wild settings. We would need new policies and guidelines between disciplines and cultures for the forthcoming global internet coverage of Earth and space. For a future work that has been ongoing, one work from our lab considers cross-orbit collaboration, where there are many satellite operators operating satellites at different orbits. No single orbit satellite could potentially meet all of the requirements. For example, geo satellites can have larger coverage but higher propagation delay. LEO satellites has lower delay but also smaller coverage. If a LEO satellite wants to provide more coverage for users in the wild, they do not necessarily need to build more ground stations or deploy more geo satellites. Instead, they could potentially collaborate with existing geo satellite operators, which can reduce the need to deploy new satellites, achieving sustainability and reducing cost. In conclusion, many of the issues we discovered in Starlink are common for most LSNs, And hopefully our observations can help optimize LSNs and help developers customize their applications that use LSNs. We have some ongoing works to consider multi-tier satellites with LEO, MEO, and GEO collaboration and how they can price accordingly in a reverse auction framework, as well as how simultaneous multi-path transmissions using ISL can improve performance and security. Additionally, we are considering that LEO satellites themselves can be mobile edge computing servers, and the challenges that may require mobility-aware cross-satellite scheduling due to the constant handovers from fast-moving satellites. LSNs are constantly evolving, and we will continue to watch for proper ISL support between LEO satellites, including MEO and GEO satellites. Thank you.
Thank you so much, Sami, and thank you, JC.